Okay, good morning children. Let us continue the chapter alternating current, and now we are going to discuss about the series LCR circuit. So in the last classes we have studied about the single circuit, that is a circuit containing the single components, that's the resistive circuit, capacitive circuit and the inductive circuit. Now we are moving to the series LCR circuit. So what is it? Here there is a component having inductance L, that is an inductor and a capacitor and a resistor are connected in series, and now we are going to find out what is the relationship between voltage and current in such a circuit. Is there any phase difference? And if there is a phase difference, what is the phase difference? How is it varying? All these things we are going to discuss now. So first let us see the circuit. So it is an LCR circuit. So it consists of an inductor, there is a capacitor and a resistor. They are connected in series. Okay. And it is connected in series across a source of voltage, alternating voltage V equal to V0 sin omega t. Okay. So here this is the inductor of inductance L, capacitor of capacitance C and resistor of resistance R. They are connected in series. So we know there is current, that is I. So there is a current I across inductor, across capacitor C and resistor R, and that I comes back. Okay. And this V, that is a potential difference, it gets divided across each component. So we can take the potential difference across the inductor, we can take it as VL, and across the capacitor it is VC, and across the resistor we can take it as VR. And where this V, that is applied potential, V is equal to VL plus VC plus VR. That is the series combination. And what is this VL, VC and VR? Let us find out what is this VL, VC and VR. What will be that? We know according to Ohm's law, V is equal to IR. Isn't it? V is equal to IR. So here the current is common, that is I. So no problem. And we have to find out, if we find out what is the opposition across each component, we can find out what is the potential difference between each component present there. So here in inductor, what is the opposition offered? What is the opposition offered called in the inductor for AC? That is known as inductive reactance. And inductive reactance is represented by XL. Isn't it? So what is VL? VL is equal to IXL. And what is XL? XL is equal to L omega. Okay. XL is equal to L omega. Then what is VC? VC will be IXC. Isn't it? What is XC? XC is capacitive reactance and it is equal to 1 by C omega. Is it? Then VR, that is the potential across the resistor. What is it? It is equal to IR. Isn't it? Because R is the opposition offered by the resistor, that is its resistance. Okay. So VL, VC and VR is the potential differences across the inductor, capacitor and resistor. Okay. So we know each potential differences and current we know, and using this we have to find out what is the current I and what is the phase difference between this resultant, that is the applied potential V equal to V0 sin omega t. And here we are using the phasor diagram to derive all these things. In the other cases, what is it? We just use the equation and substituted and simplified. And we studied the phasor diagram in each case. Using those phasor diagram, we are going to derive the condition for the resultant case. Okay. So how will be the phasor diagram? Now let us draw the phasor diagram for this combination, that is inductor, capacitor and resistor. So how the phasor diagram will be? So how will be the phasor diagram? Here we can write VL is equal to IXL, VC is equal to IXC and VR is equal to IR. We can draw the phasor diagram separately here itself. In the case of inductor, we know that voltage leads current by an angle of pi by 2. So I am taking voltage in this direction. Thus applied voltage, that is V in this direction, and we know we are considering it is moving in the, this is a phasor rotating in the anti-clockwise direction. So we will go in this direction. So it will be I, this will be I. This is VL and this is I. And this VC and I we can draw. Voltage always you take along this direction. So this will be VC and where is I? This will be I in the case of capacitor. So this is a phasor moving in the anti-clockwise direction. So here current leads voltage. And in the last case, what is it? This is VR and where will be I? It's in the same direction. I will be in the same direction. So individual phasor diagram. So I am combining this and drawing the phasor diagram. So here. So V I am taking as usual. Here I am taking V in the first quadrant here. So first here you can see that I is common everywhere. Isn't it? Here it is I, here it is I, here it is I. So I we can take here. This is the current because that is common current. So only one direction here. So that is the current flowing through the circuit. So that is I. So with respect to I, we can represent the direction of VR. So where will be VR? VR will be in the same direction. This is VR. So this one I have drawn here. And the second one is I and VC. So if this is I, where we have to draw VC, VC will be here. This is VC. That is current leads voltage. This is the direction of rotation with the angular velocity omega. And what is this angle? This angle will be pi by 2, 90 degree. Isn't it? Then where will be VL? VL leads I. Here I. So where will be VL? VL will be 90 degree more than this. So we can draw VL here. This is VL. Okay, that is all these things I combine in a single diagram. And what is this phase difference? This phase difference will be 90 degree pi by 2. Okay, so all this together it will move with an angular velocity omega. So this is the phasor diagram, all this series combination. And from this series combination, we can find out, from this phasor diagram, we can find out, first we can find out what will be the resultant of all these voltages, that is VC, VR and VL using the method of vector addition. Okay, that is three different potentials are there, voltage potential differences are there and they are in the different direction. And here we are considering this as a vector. So what will be the resultant of, what will be the resultant magnitude and resultant direction of these three vectors, that is VC, VR and VL, we have to find out. Okay, and what is the angle between the resultant potential difference and the current I? This is the current I which is flowing through this component. Okay, so how can you find out the resultant of the vectors? We studied +1 portion, we studied the law of vector addition, we studied parallelogram law of vector addition and triangular law of vector addition. So based using that law of vector addition, we can find out the resultant of these three vectors here. So for that, first you can see this VL and VC. VL and VC having different magnitude and they are in the opposite direction, isn't it? And here we are considering the condition that VL is greater than VC. This is the condition we are following. You can follow the other way like that. That is VC greater than VL. That condition also you can take. But now I am following that here VL is, I have drawn like that. VL is the larger magnitude. That is the potential difference across the inductor is more than that of the potential difference across the capacitor. So what will be the difference resultant of this VL and VC? Say this is 5 and this is 3. What will be the difference? They are in the opposite direction. So what will be the resultant of this? Two vectors are in the opposite direction. The resultant will be the difference, isn't it? And the direction will be the direction of the higher magnitude. So here the resultant of this VL and VC is VL minus VC. It will be VL minus VC. And which direction? VL minus VC will be in this direction. So here we will get VL minus VC, the direction of VL, because that is the larger magnitude. Okay. So now this vector has reduced into 2. That is, one vector is VL minus VC and the other vector is VR. Before we have 3 vectors, then we found out the resultant of this VL and VC, which are in the opposite direction, and we have followed the condition VL is greater than VC. So we got the resultant as VL minus VC in the direction of VL. Now which are the 2 vectors remaining? We have VL minus VC and VR. So how will you find out the resultant of those 2 vectors? We can apply any of the law of vector addition, isn't it? Which are the parallelogram law and triangular law. Here it is easy to follow this parallelogram law of vector addition, isn't it? Because VL minus VC and VR we can consider as the 2 sides of a parallelogram. So how will you find out? So how is the 2 sides of a parallelogram? If I am joining these 2 sides, is a parallelogram, isn't it? And what is that parallelogram law of vector addition says? Parallelogram law of vector addition says that if 2 vectors can be represented as the 2 adjacent sides of a parallelogram, then the resultant will be the diagonal, isn't it? And what will be the magnitude of the resultant? The magnitude of the resultant R is equal to root of a square plus b square plus 2ab cos theta, isn't it? Either A and B are 2 vectors. So here if I am naming this as a parallelogram A, B, C, D. A, B, C, D is the parallelogram. Where will be the resultant? The resultant will be the diagonal drawn from the same point. So this is the resultant. That is vector DB is the resultant. Isn't it? Isn't it? So we have to find out the resultant using the equation, that is R is equal to root of a square plus b square plus 2ab cos theta. So let us find out what is the resultant. So it is the result that dB is the resultant, and I am writing it as VLCR. So according to the parallelogram law of vector addition, what is it? R is equal to root of a square plus b square plus 2ab cos theta, where a and b are 2 vectors. Okay. So here which is a and b? VR is a, and we can take VL minus VC as b. Okay. A is equal to VR and b equal to VL minus VC. 2 vectors. And what is theta? Theta is the angle between VL minus VC and VR. It is equal to 90 degrees. So cos 90 comes 0. So we can omit that last term. Cos 90, it comes 0. So what is the remaining? VLCR is equal to root of VR square plus VL minus VC the whole square. VR square plus VL minus VC the whole square. Isn't it? Instead of V, it is VL minus VC. VL minus VC the whole square. Okay. So what is it? This is the resultant potential. Here we are applying a potential of V equal to V0 sin omega t, and there is a potential difference across L, that is inductor, capacitor and a resistor. Okay. Then what will be the resultant potential difference? It is AC. Okay, what is the resultant potential difference? That is equal to VLCR, and we are getting it is equal to root of VR square plus VL minus VC the whole square. Okay, then here we can substitute for VR, VL and VC. So what is VR? VR is equal to IR. So it is I square R square plus VL is IXL minus IXC the whole square. So I is common, isn't it? I square is common. We can take it outside. So it comes I root of R square plus XL minus XC the whole square. Okay. VLCR is equal to I into root of R square plus XL minus XC the whole square. And here instead of VL greater than VC, if you are taking VC greater than VL, you will get it is XC minus XL. Okay, here the condition which we are following is VL is greater than, that is the potential difference across the inductor is greater than the potential difference across the capacitor. If you are considering the other way around, that is the potential difference across the capacitor is more than that of the potential difference across the inductor, in the final equation it will be XC minus XL. That is the difference. Okay. So now we are getting VLCR is equal to I into root of R square plus XL minus XC the whole square. So from this we can write an equation for the current. What will be the current? Current will be VLCR divided by root of R square plus XL minus XC the whole square. Okay, I equal to. So this is VLCR, the resultant potential difference, and this is current. Okay, so here you can see that in series LCR circuit, the potential and current are out of phase. Okay, like the inductor and capacitor, it is out of phase. And what will be the phase difference? Is it 90 or is it 180? We can't say that, isn't it? It is coming any value. So we are taking that phase difference as phi. That phase difference as phi. So what is it? In a series LCR circuit, there is a phase difference between resultant voltage, resultant potential difference and current, and that is phi. And what is that phi? So phi, how can you find out? This is a right angle triangle. Let's go for tan phi. So tan phi is equal to the side, opposite side, which is the opposite side, VL minus VC divided by adjacent side, VR. So tan phi is equal to VL minus VC divided by VR. Again substitute for VL, that is IXL minus IXC divided by IR. I is common, it cancel, so it is equal to XL minus XC divided by R. XL minus XC divided by R, that is tan phi. So how will you find out phi? We know that phi is equal to tan inverse of XL minus XC divided by R. So what is XL, what is XC and what is R? Find out that tan inverse, that will give you the phase difference. That is the phase difference depends upon the inductive reactance, capacitive reactance and resistance of the components used in the circuit. Okay, so there is a phase difference. Understood? And look at the equation here. Come back to the equation. Thus, I is equal to VLCR divided by root of R square plus XL minus XC the whole square. So compare it with our first equation, that's the Ohm's law relation. So I is there, V is there, current is there, potential difference is there, and here in the place of the resistance, isn't it? R, what is it? We are having, in the place of the resistance, we are having root of R square plus XL minus XC the whole square. Okay, that we are writing it as Z. Z is equal to root of R square plus XL minus XC the whole square, and it is known as the impedance of the circuit. It is known as the impedance. Okay, impedance of the circuit, series LCR circuit. But in the case of a resistor, the opposition offered is purely resistance. In the case of an inductor, it is reactance. Inductor and capacitor, it is reactance. And in the case of inductor, it is inductive reactance. In the case of capacitor, it is capacitive reactance. Okay, and here all the three are there. It is connected in series, and the opposition offered, it is known as impedance. It is represented by letter Z, and what is it? Root of R square plus XL minus XC the whole square. That is, it depends upon the resistance, inductive reactance and capacitive reactance. Okay, so this is the voltage and current across the series LCR circuit. And what is the condition? There is a phase difference between voltage and current, and that phase difference phi is equal to tan inverse of XL minus XC the whole square. Okay, so we are deriving it using the phasor diagram. Here, inductor, capacitor and resistor, all the three phasor diagrams we have drawn separately. Now it is combined, and from that we can find out the resultant of the vector, that is VLCR. Using the relation, we are getting the value, and what is it? Okay, current we are getting, and it is very clear from the figure there is a phase difference between the current and voltage, and that is equal to phi. We are taking it as phi, that is tan phi, phi is equal to tan inverse of XL minus XC by R. So it depends upon the value of inductive reactance, capacitive reactance and resistance. And this term, that's the last term, the denominator term in this relation, that is known as the impedance, which is the opposition offered by the series LCR circuit to the flow of AC. Okay, so from this we have to study some more things. What is the resonance condition and all. So next we are moving to the resonance condition. So before going to the next session, write down the question, homework question. Next question number, write down. Using phasor diagram, derive an expression for impedance, derive an expression for impedance and phase angle. Derive an expression for impedance and phase angle in the case of a series LCR circuit. Phase angle or phase difference. Phase difference in the case of a series LCR circuit. Okay. In this, before going to the resonance, we have to discuss the special cases here. That is, here we have the impedance Z is equal to root of R square plus XL minus XC the whole square. Isn't it? And here we got the relation by considering VL is greater than VC. VL is greater than VC. So in such cases, that is, if VL is greater than VC, the circuit is known as inductive circuit. Circuit is known as, this is CRT, circuit, short form. Inductive circuit. and if VC greater than VL, that is the voltage across the capacitor is greater than the voltage across the inductor, what will be the equation? Such case, Z is equal to root of R square plus XC minus XL the whole square. XC minus XL the whole square, and that circuit will be known as capacitive circuit. Capacitive circuit. Inductive circuit, capacitive circuit. That is a series LCR circuit itself. Okay, if this is the condition, it is inductive circuit. So here, what is it? The current leads. That's instantaneous current will be I equal to I0 sin omega t minus phi. And here, what will be the current? I equal to I0 sin omega t plus phi. Current leads. Okay, the value comes like that. And the last case is if VC or VL is equal to VC. VL equal to VC means what? XL will be equal to XC. Yeah, XL will be equal to XC. So in such case, what will be said? Z is equal to root of R square plus XC and XL are same. So it will be 0. Z will be equal to R. That is the resistance. Resistance of the resistor. So the net opposition will be equal to the resistance of the resistor. Such circuits case is known as resistive circuit. So according to the value of VL, VC and VC, this series circuit will act as an inductive circuit, capacitive circuit and a resistive circuit. So next question is discuss the special cases. Discuss the special cases in series LCR circuit. Discuss the special cases in series LCR circuit. So this is the special cases. Okay, when it will be inductive, when it will be capacitive, and when it will be resistive. Okay. So next is the resonance condition of series LCR circuit. Resonance condition. So what do you mean by the resonance condition in a series LCR circuit? It is the condition. Resonance condition means it is the state at which the maximum current flows through the circuit. When the current flows through the circuit is maximum, we can say the circuit is, that is a series LCR circuit is in the resonance condition. Okay, so when will be the current maximum? So we can go to the equation. That is, we have I equal to VLCR divided by root of R square plus XL minus XC the whole square. This is the equation we have derived. So here, when this current becomes maximum, that is equal to the peak value, maximum amplitude or peak value, that condition is the resonance condition. Resonance, that term you heard already, like the case of the waves, you studied the resonance condition when the system becomes resonance. So to make this I maximum, what is said? This is the resultant potential, so no change. So here this should be minimum, isn't it? So what is the condition for this denominator become minimum? We can consider the condition if XL is equal to XC. That is, in the series LCR circuit, if the inductive reactance and capacitive reactance becomes equal, what is I? I will be VLCR divided by root of R square, that is equal to VLCR divided by R. Right. So what is it? There is the minimum opposition, impedance. Here the impedance becomes minimum if this is the condition. So impedance minimum, this is known as the impedance. So impedance minimum, current will be maximum. So this is the condition at which a series LCR circuit can attain the resonance condition. Okay, so we can say that resonance condition means if XL is equal to XC, the impedance of the circuit becomes minimum, and and the current flows through the circuit will be maximum. That is the resonance condition. And when this condition attained, to attain this condition, there is a frequency. Okay, that's the frequency of the that the signal will be a particular condition. If it is in a particular condition, we can attain this relation, that is XL is equal to XC. And what is that condition? Here we can write XL is equal to XC. And what is XL? We know XL is equal to L omega. And what is XC? 1 by C omega. So I am taking this omega one side. So I am getting omega square is equal to LC. And we know, so omega is equal to 1 by root LC. And what is omega? Omega is 2 pi f. So then 1 by root LC, and f, the frequency, is equal to, what is it? 1 by 2 pi root LC. So if the wave is having this frequency, which frequency? F is equal to 1 by 2 pi root LC. In such case, the series LCR circuit, XL and XC become equal. So impedance will be minimum and there will be maximum current. So that condition is known as resonance, and this frequency is known as resonant frequency. Frequency is known as resonant frequency. Condition is resonance and frequency is the resonant frequency. Okay, so when the maximum current flows, that is known as the resonance condition. And what is the resonance frequency? At the resonance condition, what is it? Through a circuit, the current will be maximum, like impedance will be minimum, current will be maximum, and that is equal to a resistive circuit. At that time it will become a resistive circuit. So the voltage and current will be in the same phase. Resistive circuit, voltage and current will be in the same phase. Okay, and what is it? Such circuits are also known as an acceptor circuit, because if we are having a circuit, series LCR circuit, and it is in the resonance condition, it is ready to accept a particular frequency from a set of frequencies, a collection of frequencies. This frequency signal will be received by that circuit. So it is known as a acceptor circuit. Okay, so series LCR circuit at a resonance condition. So write down the next question. Next question. What is the resonance condition of, what is the resonance condition of a series LCR circuit? What is the resonance condition of a series LCR circuit? Series LCR circuit. Calculate the resonant frequency. Calculate the resonant frequency. Okay, so based on this, we have to discuss about the tuning circuits. What are the tuning circuits? You know tuning circuits. There, tuning electronic devices are there. What is it? Our TV is a good example. It's a tuning device, isn't it? That is the channel we are adjusting. Using the remote, we can adjust the channel, and changing the button, we are getting the different channel. And radio is a tuning device, isn't it? I think you are familiar with radio. When we are rotating the knob, what is it? We are getting the different stations, isn't it? We have Thiruvananthapuram, Kozhikode, so many stations are there. So and now it is that FM channels are there. So everything we can receive by changing the knob. So what are you doing while changing the knob? By changing the knob, you are adjusting the frequency. I told you this series LCR circuit at the resonance condition, it is known as the acceptor circuit. So we are, by adjusting the knob, we are making it in the resonance condition. So at that particular condition, at which frequency it is become resonance, that frequency will be accepted from the set of signals. Okay, so it is a very important one. LCR circuit, series circuit, it is having a very important role as the tuning circuit. So it consists of, that is tuning circuit, it is the parallel combination, it is a parallel connection of an inductor and a variable capacitor. So while turning the knob or what is that, adjusting the channel, what are you doing? You are just adjusting the capacitor, you are changing the value of the capacitor. So once you are changing the value of the capacitor, look at the equation, what happened as C changes, what happened, this frequency changes. So to which frequency it is become resonance, that will be the frequency, maximum frequency, and that signal will be received by the system. Okay, if you TV or radio, whatever it is, just understood. So that is how we can use this series LCR circuit as the tuning device, in the tuning devices. So it is, the connection comes like this. Inductor, and here the variable capacitor, and this is to the receiver. Okay, this is to the receiver. Okay, receiver antenna. And what is happening while tuning? We are changing the value of the capacitor. So as capacitance changes, the frequency, the resonant frequency will be 1 by 2 pi root LC. There is a frequency called resonant frequency. So for that frequency, many voltages will be there in the different signal, means there are different voltages, and from that which voltage the current through the system is maximum, that will be received and it will reach we are receiving that signal. So that is the tuning device. Okay, we are using this series LCR circuit for tuning. Okay, so write down the next question. Next question. Explain the working of a series LCR circuit. As a tuning device, as a tuning circuit, or how it is helping in tuning. How is it helping for tuning? So the next quantity related with this series LCR circuit is sharpness of resonance and Q factor. From resonance condition we know. So what do you mean by the sharpness of resonance? So what is the resonance condition? For a particular frequency there is a maximum current, isn't it? So here if we are plotting this frequency and current, here we can take frequency and current. So the frequency here, it is increasing from a particular value, that is 0, and it is increasing and it reaches a particular value, that is our resonant frequency. Take it as omega r. Then what happened? From that maximum, again what happened? It decreases, isn't it? That is the current flows. This is the value where there is maximum current. So both sides the current will be less than that. So if you are plotting the variation of current with the frequency, we can see that the current will go like this. It will go like this. That is the maximum value will be attained. For this particular frequency called the resonant frequency omega r, and this here the current will be I0. Okay, so according to the equation we know current I is equal to, what is it, V divided by root of r square plus xl minus xc the whole square. So according to this xl minus xc and xc minus xl, there is a variation, current will be changing, and for the minimum position, that is the minimum resistance R, the current will be maximum, and that is the resonance condition. and it is attained for a particular frequency, that is omega r. So we can write the equation as I is equal to V by R at the resonance condition. Okay, and here also the current changes according to R. If a circuit containing small resistance, if R value is small or R value is big, accordingly what happened, the current also changes, isn't it? So here I am considering that here the value of resistance R is low value of resistance, very small resistance. And if R is increased in that LCR circuit, say for example here it is 1 ohm, for example R is equal to 1 ohm, and the next circuit we are taking R is equal to 2 ohm. So what happened to the current? Current will be decreased. So we can say that we will get the curve like this. See, so here R is more value of resistance. And again this R is increased, say 5 ohm. So what happened? What happened to the current? It increases and it attains a maximum and it decreases. So what happened? The curve become flattened. So even at the resonance condition, according to the value of R, there is a variation in the peak value of current, maximum value of current. So this sharpness, that is this peak, that's a maximum one. Okay, so that is known as the sharpness of resonance. So when it will more sharp for less value of resistance. Okay, so the input resistance in the circuit, if the resistance is less, the sharpness will be more. And the sharpness is measured by a quantity that is known as the Q factor. Sharpness is measured by a quantity that is known as the Q factor. So what do you mean by the sharpness? It is the term represent sharp, where the peak is sharp. So what is the condition in this circuit to get the maximum current? In the series LCR circuit, we have to use low resistance, then only we will get the maximum current. So that is defined, that is determined by the factor called the Q factor. So we can calculate what will be the Q factor, and to get the Q, according to the Q factor, we can choose the component, that is L and C. So that is the frequency. It depends upon what? 1 by 2 pi root LC. So what is the value of L and C? We can choose according to the required Q factor for getting the maximum current. So this represents the sharpness. According to the value of R, that is the resistance, the curve becomes flatter. That is, it becomes less sharp. That is, the maximum current decreases. Okay, so we need the maximum current, and in that case the resistance should be less, and that is known as that is defined as the sharpness of the resonance, and it is measured by a factor called the Q factor. It is a dimensionless constant. Okay, dimensionless quantity is Q factor. So what is Q factor? How can we define Q factor? So this Q factor, it is defined as, what is Q factor? It is the measurement of sharpness. And how is it? It is defined as, you can see that from that 3 curves, I have taken this curve only. This is for less value of R. Okay, R is less here. I0 is the maximum. And I have considered 2 more frequencies here. That is, one is omega 1 and other one is omega 2. And where is this omega 1 and omega 2? At omega 1 and omega 2, the current becomes I0 by root 2. And what is I0 by root 2? It is the RMS value of AC. Okay. So at which frequency this current becomes the RMS value, that 2 frequencies have taken here, that is omega 1 and omega 2. So we can define Q factor. Q factor, it is the ratio between the resonant frequency omega R and the difference between two frequencies at which the current becomes the, or 1 by root 2 times current becomes the RMS value, or it is 1 by root 2 times of I0. So that quantity, it is known as the Q factor. So here omega and omega, so no unit, no dimension. Okay, so what is it? Q factor is defined as it is the ratio. So how can we measure the Q factor? What is it? It is the ratio between two frequencies. Which are the two frequencies? One is the resonant frequency and the other one is the difference between two frequencies. And what is the difference frequencies? That frequencies are the frequencies at which the current becomes equal to the RMS value, or 1 by root 2 times the peak value. Okay, so Q is equal to omega R divided by omega 1 minus omega 2. And what is this omega 1 and omega 2? Here there is a small difference. We can take this delta omega this side and delta omega this side. So from this we can write omega R divided by 2 delta omega. Here it is omega 1 is equal to what? Omega R minus delta omega, and omega 2 is equal to omega R plus delta omega. So substituting and simplifying, you will get it is 2 delta omega. And this 2 delta omega, it is known as the bandwidth. It is known as the bandwidth. You have heard about this, bandwidth, isn't it? So in the radio station or TV, you know that if you are tuning this Asianet channel, you are getting only Asianet. That's signal from that channel. Surya, that particular one. Radio FM, the 94.5. What is it? When you are tuning, you are getting the signal from that channel only. So what is it? That is from the station, wherever it is, TV broadcasting or radio broadcasting, wherever it is. For each channel, what is it? There is a particular band they are allotted. So they are sending the signal within that band itself only. Okay, that particular frequency or particular wavelength. They can't use more than or less than that. So they are sending the signal in that particular frequency. So that is known as its bandwidth. For example, 250 Hz to 300 Hz. Say it is the bandwidth of a particular station. So what is it? They can make the signals with the frequency in between this, that is 250 to 300. Okay, and in that maximum, they can send maximum in between this, they can send the signal, and they can't go for 249 or 301. Okay, 49 or 301, that will be allotted for the other channel or another this station. The same thing is happening in the case of our SIM also. Our SIM card means what is it? It is a particular frequency. So from our phone through that SIM, the signal is going with that particular frequency or wavelength. So that is received. If somebody is using the other one, what happened? It won't work out, isn't it? So each frequency or each bandwidth is there. For each signal, there is a bandwidth. So they are sending the signal in that particular bandwidth. Understood? So that is the bandwidth. That is the minimum and maximum value of frequency. It is known as the bandwidth. Okay, so from that bandwidth we can find out the Q factor. So what is it? Omega divided by omega 1 minus omega 2. So that is known as the bandwidth. See, this is the thing. Okay, the signal is sent in that particular frequency. Understood? So that is the Q factor. And in this Q factor, some equations are there in terms of resistance, inductance and capacitance. So we have to see what is the equation. So before that, write down the question. What is meant by sharpness of a resonant circuit? What is meant by sharpness of a resonant circuit? Next question. Define Q factor. Define Q factor and bandwidth. Define Q factor and bandwidth. I think this is the fourth question in this session, isn't it? Q factor and its bandwidth. Expression for Q factor, that is Q is equal to this. We have got the from the definition, omega r divided by omega 1 minus omega 2, or omega r divided by 2 delta omega. Omega r is the resonant frequency and this is the bandwidth. And in terms of inductance and resistance, omega r L by R, that is L omega by R. and here omega is omega r, so it is omega r L by r. So in that case what the capacitance is not there, and here 1 by omega c into r. Okay, instead of omega it is omega r, and it is 1 by r, simplifying it is 1 by r root L by c. That derivation is not required for you, so you just study the final equation for this Q factor. Okay, so problems comes if resonant frequency and bandwidth is given, you can use the equation to find out the Q factor. If inductance and resistance is given, you can use this equation to find out the Q factor. Capacitance and resistance is given, you can use this equation, and these three are given and omega r is not given, you can use this equation to find out the Q factor. So write down the last question. Write the different expressions for Q factor. Write the different expressions for Q factor. And today we discussed about the series LCR circuit. In series LCR circuit, what is the resultant potential and what is the resultant opposition, that is known as the impedance. What is its expression and what is the phase difference between the voltage and current. Then we have seen what is the resonance condition and resonant frequency, and that resonance condition, how it is helping for tuning and how is it useful in the tuning devices, and sharpness and Q factor. So all these questions answer you write and submit to me, okay, on the same day itself. Okay, thank you.